Navigating an aircraft safely from point A to point B is a massive geometric problem. It requires tracking a high-speed object across an oblate, spinning, magnetic spheroid, utilizing only localized sensor readings and distant electromagnetic signals. Mastering this environment requires a pilot to integrate three distinct disciplines: general navigation, aircraft instruments, and radio navigation. Every input a pilot receives contains inherent physical distortions. Two-dimensional paper maps warp geographic reality. Minor changes in air density falsify airspeed measurements. Atmospheric boundaries physically bend radio signals away from their true paths. Modern flight relies on continuous sensor fusion, a process of constantly comparing and correcting flawed data streams against one another to find an exact position. To achieve absolute coordinate certainty, a pilot must sequentially master the geometry of the Earth, the internal physics of the aircraft, and the behavior of external electromagnetic waves. The geometry of flight begins with the planet's movement. As Johannes Kepler's laws established, the Earth revolves around the Sun in an elliptical orbit. This model illustrates how the Earth's 23.5-degree orbital tilt drives seasonal variation and defines precise periods of atmospheric lighting. Twilight is categorized by strict mathematical limits based on the Sun's depression angle below the sensible horizon. 0 to 6 degrees dictates civil twilight, 6 to 12 is nautical, and 12 to 18 is astronomical. Translating this three-dimensional oblate spheroid onto a two-dimensional paper chart creates an unavoidable cartographic dilemma. Mathematical distortion is required to make the map flat. Mercator wraps a cylinder around the equator, while Lambert's places a cone over the pole. Because of this geometry, a great circle curves on Mercator, but plots straight on Lambert. Conversely, a rhumb line is straight on Mercator, but curves on Lambert. Pilots use mathematical formulas for convergency and conversion angle to calculate the exact difference between the theoretical great circle route and the flyable rhumb line heading. Every paper chart geometrically distorts the surface of the Earth. Navigating over long distances requires calculating the exact degree of that distortion to find true direction. Before advanced electronic sensors existed, aviators relied on dead reckoning, the process of estimating a current position by advancing a previously known fix over elapsed time. The wind triangle isolates true airspeed and heading, then factors in wind velocity. Aggregating these vectors reveals the actual track and ground speed. However, because dead reckoning relies on estimates, any slight miscalculation creates an expanding cone of uncertainty. Dead reckoning provides a necessary logic loop for basic routing, but geographic drift forces the aircraft to rely on physical onboard sensors for correction. Those physical corrections begin with the air data system, which captures raw atmospheric data through the aircraft's pitot tube. The system measures the total pressure of ram air, subtracting ambient static pressure to find dynamic pressure, or indicated airspeed. This data is then filtered through mathematical corrections for instrument placement, compressibility, and air density to calculate the exact true airspeed. Spatial orientation relies on mechanical gyroscopes, utilizing rigidity in space to stabilize the spin axis and precession to react to forces. However, because gyros maintain rigidity relative to space, Earth's physical rotation beneath them causes an apparent tilt known as apparent wander. Pitot tubes and mechanical gyros provide instantaneous autonomous feedback, but they are bound by internal friction and atmospheric variations. They require a higher tier of mathematical integration to maintain long-term accuracy. Modern aviation replaces mechanical gyroscopes with the inertial navigation system, utilizing solid-state accelerometers and laser ring gyros. This graph demonstrates the core mathematical principle of the INS, double integration. By tracking exactly how fast the aircraft accelerates over time, the system calculates velocity. Integrating that velocity over time yields the exact geographic distance traveled along an XYZ grid. The INS tracks precise latitude and longitude entirely autonomously. It requires no external signals and is immune to weather interference or radio jamming. Microscopic alignment errors multiply through the integration process into miles of geographic drift. To arrest this drift, the aircraft must seek external verification. Pilots verify their internal calculations using external radio signals. historically starting with the low-frequency non-directional beacon and the onboard automatic direction finder. Low-frequency signals suffer from coastal refraction error. When radio waves cross from land to ocean, surface conductivity changes cause the signal to bend acutely. Pilots mitigate this by selecting beacons whose signals cross the coastline at a strict 90-degree angle. To bypass low-frequency errors entirely, aviation developed the Very High Frequency Omnidirectional Range, or VOR. VOR uses phase comparison. A ground station broadcasts a constant 30 Hz reference wave in all directions, and a highly directional 30 Hz variable wave that rotates. Measuring the phase difference between these peaks instantly translates into a specific 360-degree magnetic bearing. VOR provides highly accurate angular tracking, but it operates on very high frequencies, creating navigational dead zones over oceans and behind mountain ranges. To overcome line-of-sight limitations, modern aviation relies on orbital external references, global navigation satellite systems. These systems operate on the principle of trilateration. The aircraft's receiver calculates its exact distance from multiple satellites by measuring the precise time delay of incoming pseudo-random noise codes. To lock in a definitive location, the system requires 4 satellites. 3 intersecting spheres resolve the physical 3D spatial coordinates, while the 4th satellite corrects the inherent timing error in the receiver's internal clock. All 3 navigation pillars, mathematics, internal instruments, and external radios, converge in the modern electronic flight instrument system to enable area navigation and required navigation performance. The flight management system continuously cross-checks dead reckoning computations against INS accelerations and GPS updates, isolating and discarding any erroneous data. Spatial certainty in a modern cockpit is the product of a rigorous, self-correcting ecosystem where Earth geometry, the onboard physics, and orbital signals constantly validate each other to ensure absolute precision.